Right, this video is about measuring populations, or the abundance of organisms, both sessile and motile organisms, and it links to required practical 12, which is the effect of an abiotic factor on the distribution of organisms. So you need to be aware of some different techniques, the advantages of them, and which technique you'd use when. So one technique you can use is frame quadrats. They might be what you're more used to using at school. We'll use them for required practical 12 as well. You can get different size quadrats. Some can be very small, some can be very large, and it depends on the type of organism you're investigating. Also the number of quadrats as well. If you've got larger quadrats, also the larger number of quadrats, it makes the results more representative and more reliable. And also you can use random sampling to avoid bias, although you can use frame quadrats with a systematic sample as well, which we'll look at later. So we've already looked at random sampling as a way that you can use to see, for example, if the height of different dandelions in a field, but you can also use random sampling to measure the abundance of different species as well. So you would use random sampling for required practical 12, which, just a reminder, the effect of an abiotic factor in the abundance of, and an abiotic factor is a non-living factor, so it could be things like temperature, sunlight, pH, rainfall, things like that. So random sampling could be used if you wanted to see the effect of north or south facing fields, for example, and whether the angle of a slope is north facing or south facing can affect things like sunlight or temperature. And you could see if that affects the abundance of a species, for example plantains. And this would be the method that you would do in both areas, and then you can compare the results afterwards with a statistical test. So this avoids bias. Remember, you grid the area with rope or tape. Use a random number generator. Place the quadrats at your intersections, at your coordinates, and then you count the number of individuals. If we're in the example from the first slide, it was buttercups. You count the number of buttercups in each quadrat. You repeat it many times to make the results representative and reliable, and you can calculate the mean per quadrat. The final thing you might want to do after that is then scale it up to estimate the population of the whole area. So you could work out the mean per quadrat and then times that by how many quadrats would fit in the area. So if your quadrat was 1 metre squared, that's quite a large quadrat, but if your quadrat was 1 metre squared, you can then multiply that by the area metre squared of the field. There is another technique called a point quadrat as well. So a point quadrat is where you have these pins, and then you let them fall. You place them at the coordinate, and you let these fall. And you can use this measure here for percentage cover. So the number, if it was buttercups again, the number of pins that hit buttercups divided by the number of pins when you let them fall in total, times by 100. And this is a better technique than the frame quadrat for estimating percentage cover, rather than sort of estimating percentage cover, just looking at the frame, the square frame. This gives you a more sort of quantifiable way of saying, well, each of those pins, if you had 10 pins, each of those pins represents 10%. So it's more of a yes or no rather than estimating. It's less subjective. Another type of sampling that's not random sampling, systematic sampling. So this can be used to determine the distribution of species. But it's important you know when to use systematic sampling and when to use random sampling. So systematic sampling can show how population changes as the habitat changes. So for example, going from the sea across a sand dune, so it's going from where it could be really salty near the sea to where it gets less and less and less salty, the water or the soil, as you go away from the sea. So that's showing how the habitat changes, how that could affect the population. You could for roadsides, so here we've got the road, and different abiotic factors could change as you move away from the road, and you can lay out the transect, which we'll come on to in a minute, away from there. rocky shores, another really good example for using systematic sampling. Again, you've got the low tide and then you've got high tide, and the number of hours covered by water could be the abiotic factor, and what effect that has on the abundance of different species of seaweeds, for example. So the technique you need to be aware of for systematic sampling is a belt transect, and it can be used for required practical 12 to measure the abundance of organisms as your abiotic factor changes with distance. So in this example, we've got a rocky shore. So we've got the sea down here up to you can see sort of the grass at the top of the beach, so the top of the rocky shore up there. So down here will be covered by water more than up here. So you'd expect to see different species as you go from areas that are more covered with water for more hours of the day to less hours of the day. So you lay your transect across, going from the bottom of the shore that's covered in water a lot to the upper shore where it's not covered with water for very much, and you systematically place your quadrats, so at regular distances. So every metre, every 2 metres, it would depend on the length of your transect. And then you can estimate the percentage cover or count the number of individuals in each quadrat. That depends on what you're looking at, which is more appropriate, which we'll come on to in a second. And you can have several transects going across at different points along the shoreline to get a large sample to make it representative. That's a way that you can do repeats with this. So it's important you know when a random sample is appropriate and when a transect or a systematic sample is appropriate. So I just mentioned about counting numbers of species and measuring percentage cover. So which is most appropriate and when? So if it's not too difficult to count the number of species, then that's the best method to do it. So you might be able to count the number of dandelions in a quadrat, for example. But could you count the number of algae? Could you count the number of grass in a quadrat, for example? You probably couldn't, or if you tried, it would not be very accurate. So to avoid that, you can use percentage cover instead when there are too many to count, and if you did try to count it, the results would be inaccurate. So this is something that can be done after doing a belt transect and measuring percentage cover. So here we've got the lower shore, here we've got the top of the shore, and we've got time underwater per day. You can see, and this is called a kite diagram, and it's a graphical representation of the percentage cover. So you can see that this species first starts to appear at this point here, and has finished appearing on the shore at that height of the shore, and this species first appears here, and then is not found anymore at that point on the shore. And this species is most abundant with 4 hours under the water. So the techniques that we've looked at so far have been for measuring sessile organisms, so ones that don't move. But if we're going to measure the abundance or the population size of animals that are motile, that can move, we need a different technique. So mark-release recapture is a technique that's used to estimate the size of populations. It's not an exact it doesn't give an exact population size, but it does give an estimate. So what you would do is you capture some individuals within the population. You'd mark them, for example, a tag on this bird, or you could add a bit of nail varnish to the back of a snail, whatever technique, and we'll come on to in a minute what the limitations of that are, and then you release them into the wild, and then after a period of time you capture the individuals again, you count how many are marked and how many are not marked. And there are quite a few assumptions to be made with this, and you could be asked questions on it. The first one is that enough time is left after releasing the ones that you've marked for them to randomly mix within the population. Okay. The second assumption is there's no migration and there's very few births and deaths. So it's sort of a static population. And the other one that's also a common exam mark point, is the method of marking does not affect the chance of survival. So things that could affect the chance of survival are maybe the mark, if the mark increased the chance that they would get eaten. So you wouldn't want necessarily to paint on the back of a snail something that makes them less camouflaged. So birds might be more likely to eat them, because that would affect their chance of survival. Also, the mark can't be toxic, so it can't kill the animals that you put it on. So the how you mark them cannot affect their chance of survival. And in a question, it's better to give an example, like it might make them more likely to be eaten or might be toxic. So this is an important question. You could be asked, and this could be worth 3 marks, how you'd estimate the population size of a motile organism. So that's an organism that moves. So first of all, you collect your sample. You may have to suggest a suitable way of doing that. For example, a net for catching butterflies, but link it to the question. Then mark the animal, and again you might have to suggest a suitable way of marking them, but remember it can't increase the chance of predation and it can't be toxic. Then release them back into the wild. You've got to remember leave enough time for them to evenly distribute within the population. And you recapture a second sample, and then you can estimate the population size using the formula: the number in the first sample times by the total number in the second sample divided by the number that you counted that were marked in the second sample, so i.e. the number that were recaptured. So in this example here with stag beetles, so 39 beetles were captured and marked in the first sample. They allowed 30, this is a limitation here, that's not long enough really to allow random mixing within the population so they're evenly distributed. But anyway, 35 beetles were captured and 20 had been marked. So number in the first sample, 39, times by the number in the second sample, 35, divided by the number which were recaptured or marked in the second sample, which is 20. So an estimated population size of 68 beetles in that habitat.